dear colleagues and everyone online or on site or yeah. So welcome to the I believe this is number 63rd Open Seminar in Frontier of Nuclear Physics, and probably this is the last one in this year, 2023. So and it's our great pleasure to have again Nagae-san from Kyoto University to give us the seminar again, talking about the J-PARC strangeness physics. This seminar series is organized by the Institute of Modern Physics, the Key Lab of Nuclear Physics and Ion Beam Application at Fudan University, and the Shanghai Research Center for the Theoretical Nuclear Physics, NSFC. It's sponsored by the Journal of Nuclear Science and Techniques, and also live streamed on the koshare.com. So welcome, Nagae-san, please.
Okay. Good morning, everybody. It's my great pleasure to have the second seminar in this Yeah. So today I will discuss about the J-PARC strangeness physics program. We are now going on at the Japan Proton Accelerator Research Complex, J-PARC. So this is the menu of today's my talk. After a short introduction of the J-PARC facility, I want to give you several topics on the strangeness nuclear physics and a little bit particle physics. As for the strangeness nuclear physics, today I want to touch on cascade hypernuclei and new spectrometer. We are now constructing strangeness -2 spectrometer. And also our next program on the high resolution pi-k spectroscopy to achieve better energy resolution of the 1 MeV. And also I would like to discuss about kaon nucleus cluster experiment at the J-PARC. And also, I would like to briefly touch on our new project. I mean, we are going to extend our hadron hole experimental area by doubling the area so that we want to have more physics programs. So I would like to introduce you some of the topics which we can do for after this extension of the hadron hole. So anyway, our hadron hole was constructed. It's completed in 2009, and 2000. Looks my computer is somehow stuck. But okay. Yeah, okay. So this is a picture in 2009, just after the completion of the construction of this hadron experimental hole. So our beam times just started this 2009. We celebrated such a large number of people who are worked for the hadron hole construction. Okay. So this is the view of the whole J-PARC facility, which is located in the east of the Japan. The sea, you can see here, this blue colored region is the Pacific Ocean. And our beam starts from somewhere around here at the left side of this picture. From the line, we have a proton line here, which accelerates H minus ion beam up to 400 MeV. Then that beam is injected into the 3GeV rapid cycling synchrotron shown here. And this 3GeV machine, the beam is transferred to the what we call the MLF, Material and Life Science Facility, which is shown here. In this large experimental area, we have a neutron beam and also a muon beam, so that we can get we can have material science in this experimental area. And that is a 3GeV machine. Proton is used to produce neutron and the muon. And then the 3GeV beam, part of the beam will be injected into this main ring. The radius is about 1 kilometer here, this orange curve. And we have two extraction points. One is for the our hadron hole here, producing the several secondary kaon beams. And also we have another extraction point here. It's a neutrino beam line. So we share the beam from the main ring with neutrino and hadron. Okay. So, and by using this main ring, we have a lot of experimental programs, both on the hadron experiment and also for the neutrino experiment. And nowadays, we also have a muon rare decay experiment and so on. So this is a rather busy view, but you can see this is the neutrino beam line for the T2K experiment, this orange colored one. And also in the hadron hole, we have a Koto experiment that is the K-long to pi 0 nu bar such experiment, this reaction. And also we have a hypernuclear physics program, of course, in the hadron experimental facility. Then as I mentioned, we also have a muon experiment. It's a mu-E conversion experiment called COMET experiment. And also hadron hole, not only the hypernuclear physics, but also we have hadron spectroscopy or such kind of program also in the hadron experimental facility. And recently also we have a program of the muon G-2 experiment. That is not in using the main link, but using the MLF muon beam. And also there are several other newcomers of the neutrino experiment and so on. And here I listed up several results obtained in the recent few years from the main ring facility. In the case of strangeness -1 hypernuclear physics program, last time I just a little bit discussed, but anyway, S equal -1 nuclei, we have observed large charge symmetry breaking in the E13 experiment by Tamura-san's group. Also, strangeness -new nuclei in the E07 experiment, that's emulsion experiment. They observed a lot of new information on the cascade hypernuclei and also double lambda hypernuclei, such as strangeness -2 nuclear system. New information was obtained in the hadron hole. And also, recently, the sigma and the proton scattering measurement was carried out by the Tohoku Miwa-san's group. And they improved the statistical accuracies. Very good data was taken, which is shown here. This yellow curve and their experimental data. And by comparing the old data, it is a very great improvement of the statistics, but still we might need a lot of sigma p scattering data in order to pin down what is the origin of the repulsive core. And also, here in the hadron hole, we have another series of measurements that is to search for the K-PP chaotic cluster events. And we have a very prominent peak structure in E15 on the K-PP, as well as E27 sigma 0p signal is observed like this one. So that the kaon cluster K-PP looks to be bound by the strong interaction. Okay, then I want to discuss the cascade hypernuclear system, whether it is really strongly bound system or the shallowly Coulomb assisted state that I want to discuss a little bit here. So this is the summary of the emulsion data at this time we observed, and roughly speaking, there is two clusters of the cascade hypernuclear events. This green band and orange band, and this axis is binding energy of the cascade, so that that in the case of the cascade, we have a cascade minus, so that Coulomb potential still exists, so that the binding energy of the less than 1 MeV, these could be Coulomb assisted bound state of the cascade nuclear system. So that, but it's not the Coulomb, purely Coulomb, but Coulomb plus strong attraction. So these we call the Coulomb assisted cascade events. Here the binding energy of cascade is about 0 to 1 MeV, these cluster of events. So we can say the cascade nucleus potential seems attractive. That is quite sure. I mean, attractive means not only the Coulomb, but also we have a strong interaction attraction. But in addition to these Coulomb assisted events, it looks just one or two events, but the binding energy of the cascade, there is two cluster of events telling us about 6 MeV, very large binding energy for the cascade minus particle. This is quite confusing. I mean, not based on so far we know about the other hadron signals. The case for the cascade binding energy of 6 MeV is looks to me a little bit too large. So that and that puzzle is also suggesting here there is also the stop cascade minus event. I mean, cascade minus is Coulomb only Coulomb interaction. We can have a bound state, so that just so that those atomic bound state of the cascade minus, we used to say, or the theorists used to say, that those are bound, those states are bound from the atomic 3D state or the 2P state. 3D state or 2P state. And so that if we have this 1s strongly bound sigma cascade minus state, then transition of the 3D or 2P atomic absorption strength should be very strong, so that X-rays from the cascade minus atom should be observed with such a measurement of the cascade minus atom. But there is such a search of the atomic X-ray for the cascade minus, but we cannot observe this atomic bound state transitions of the cascade minus atom. So that this is currently a puzzle for both theorists and experimentalists. At least the search for those X-rays are ongoing at the J-PARC. So further study information could be obtained in the coming beam time. And also for the proton and cascade minus interaction, we have very good data from the ARIS experiment for the femtoscopic study to extract interaction strength of the proton and the cascade minus. And that is also telling us proton and cascade minus interaction is really attractive. So that in this sense, the observation in the emulsion and this femtoscopy analysis looks consistent, but it's the width of the state, I mean transition rate, which I showed you for the cascade minus atom, that is again here is also the puzzle still holds for this case also. So that I mean P cascade minus interaction is such a attractive potential, then we should observe the X-rays as I mentioned. Okay, then I would like to introduce you our strangeness -2 spectrometer in the hadron hole extension. This is should be a major upgrade of our detector systems for the coming several years. Okay, so and in this case, the cascade minus bound state is looked for by using the S-2 spectrometer, and this is the theoretical model calculation showing the cascade minus bound state. Those two peaks, in this case, oxygen, target is oxygen 16, so that we have two peak structures shown here. And also we have a cascade minus bound state, which corresponding to these peak structures. And these peaks are for the cascade bound state peak structures, and these ones are double lambda peak structures. S lambda, P lambda state is shown here. So this tells us that there could be a strong coupling between the cascade minus and the double lambda system in between these regions. I mean, mass difference of the cascade n to double lambda is only 28 MeV, so that those energy levels of the double lambda system, excited level of the double lambda system, and the bound state of the cascade system very energetically so close in the cascade hypernuclei and the double lambda hypernuclei. So this kind of baryon coupling effect could be observed in the double lambda and cascade hypernuclear system. And okay, I skipped this one. So yeah, so this is the S2S spectrometer system just installed in the hadron hole K1.8 beamline. Experimental target is installed somewhere around here, and we have quadrupole the magnet here and dipole magnet here, and tracking detectors are followed, so that this spectrometer system is a very large magnet, and just we started beam commissioning last June this year. So in the case of first experiment using this S2S spectrometer, we plan to have a missing mass spectroscopy on the E70 experiment. We have K- beam 1.8 GeV/c hitting on the target. Then K+ is emitted in the forward direction. The momentum transfer is about 500 MeV/c, so that spin stretched configuration are preferentially produced in this reaction of the K- K+ by using the S2S spectrometer. This is whole picture of the beamline spectrometer and K-on spectrometer S2S. The energy resolution we are in our design, we aim at 2 MeV energy resolution for the cascade hypernuclei, and also this spectrometer has a rather large solid angle of 60 millisteradian. So this is again the last part of the detector system. Okay, so this is the present hadron experimental area about 50 meter by 60 meter long hadron experimental hole. And as I said, this K1.8 beam line, we have a high intensity K minus beam here, and S2S is now already installed in this area. And our aim, our plan to extend this hadron hole is to almost double the area which is shown here, so that currently we have one production target T1 here, and secondary beam lines are shown this way. But in the extension, we have two production targets shown, T1 and T2, so that roughly speaking, the number of beam lines just doubled, so that we have, at this moment, we have 1, 2, 3, 4 secondary beam lines, but by extending the hadron hole, we have 1, 2, 3, 4, 5, maybe 5 secondary beam lines in this extended hadron hole. So this is the real situation of the how many secondary beam lines we will have by extension of the hadron hole here. So presently we have K1.8, K1.8 BR, and high P, and K-rail, and comet muon line. But in addition to these 1, 2, 3, 4, 5, we have 1, 2, 3, 4, 5, 6, 7, at least 7 new beam lines will be constructed, so that we have a large potential to conduct a new type of the beam lines, and physics plan will be available. Like K10 beam line, that this is a 10 GeV over C K-on beam line for the cascade, high mass cascade excitation program can be only done at the K10 beam line. Also, we have upgrade of the K-long beam line and comet beam lines as also. And our strangeness hypernuclear program is HIHR beam line, high intensity, high resolution beam line is our important beam line for the strangeness hypernuclear program. This is the idea of or design of the HIHR beam lines spectrometer also. This beam line use the technique of the dispersion matching technique, so that the upstream part of the beam and downstream part of the beam, the dispersion is quite matched to each other, so that without having the tracking detector system, we can get high intensity beam, pion beam, and good energy resolution from this kind of dispersion matching technique. Having our goal of the momentum or the energy resolution would be, say, less than 400 keV or so. So that in the case of the lambda hypernuclei, we have a very good energy resolution by using this HIHR facility. So that I'm sorry, I missed one. I'm sorry. Yeah, anyway, so this is the high intensity, high resolution beam line when the hadron hole is extended. We would like to install these facility beamline spectrometer system with first priority. Then I come to the last topic of the kaon nucleus bound system. The kaon bound system, we have this lambda star nucleon pair. Lambda star is lambda 1405, the excited level of the lambda ground state lambda particle, so that lambda star n could have a bound state of the lambda 1405 and nucleon, and that system decays into the sigma n or the pi sigma n. Those are the decay channel of the lambda star n system. So that many of the experiments to look for this lambda star n bound state was tried in the J-PARC facility also. So that and this one is E15. These are most promising candidate of the signal of the lambda star n bound state. This axis, horizontal axis, is the invariant mass of the lambda star n. Is this axis, and this axis is the momentum of transfer for the lambda star n system. And this red colored events shown here is cluster of the lambda star n events. I mean the lambda star n bound state candidate, which if we plot this area onto the invariant mass of the system, this is the picture from those events. This red arrow shows the threshold of the K bar NN system. So that little bit in the bound state region, we observed this large enhancement of the invariant mass event here, so that from this fitting of the red curve shown here, we estimated the binding energy of this K bar N system is about 40 MeV, and also the width of this signal is quite large, I mean 100 MeV. So large width, but significantly large bound energy. This KPP system is observed in this picture. The similar data is also obtained in the E27 experiment, which is a little bit in the early stage of the J-PARC facility. Data was taken, shown here. Okay, so here I just I want to introduce you the coming few years what we are going to do in this hadron experimental hall. From the April to May, we installed a new power supply for the mainly for the neutrino experiment, but also which benefits the stability of the hadron hole beam lines also, so that early in the 2000, we have a rather long shutdown for the maintenance of this power supplies. And for the slow extraction mode, we will shorten the flat top part of the beam from 5.2 seconds to 4.3 seconds, so that we can have a shorter repetition rate, so that in the hadron hole, we immediately want to carry out 60 kilowatt beam power, and that will be soon improved up to 80 kilowatt for the proton beam for the slow extraction. So that we are hoping to have in 1 or 2 years. Then before the hadron hole extension, we have a good program for the S2S, S-2 spectrometer system, and also cylindrical drift chamber system, which is a KPP experiment for the KPP experiment. And all of those KPP and cascade nucleus, all of those are related to the high density neutron star matter physics, so that if we can have a very good high pi k spectroscopy with a very less than 1 MeV resolution, then we can have an estimate on the repulsion in the high density matter, so that so those three body force effects or those kind of things can be studied with the S2S spectrometer with 1 MeV energy resolution. This is the theoretical estimate of the what kind of energy spectrum can be done with the this is the pi k reaction, and these spectrum of the lambda hypernuclei tells us the lambda nn three body force effect or so on. If we can achieve 400 keV energy resolution, and this will show us the inside of the neutron star what kind of strange matter could be existing or not. So this is our immediate goal for before the hadron hole extension. So that, but after the hadron hole extension, the HIHR beamline will enables us to have a 400 keV energy resolution. That's quite enough to carry out the spectroscopy of the 400 keV. But before that, we believe that our S2S spectrometer system, by using it, we can reach to the 1 MeV energy resolution, so that this kind of spectrum can be obtained before before the hadron hole extension program is going on. Okay, so and one more thing is one thing we would like to have is lambda sigma mixing effect. Lambda sigma mixing effect can be studied with neutron-rich lambda hypernuclear spectroscopy. You know, by using the pi minus k plus reaction, we can reach to the neutron-rich lambda hypernuclear state. But so far, nobody succeeded to reach such a neutron-rich lambda hypernuclear state so far. So I believe if by using the S2S spectrometer, we can have a very surely good spectroscopy of the neutron-rich lambda hypernuclei. So these are our experimental program in the coming 5 or several years, I believe. And So of course, the double lambda hypernuclear spectroscopy and the cascade hypernuclear spectroscopy, those can be done with the strangeness -2 spectrometer for sure. And also the H-dye baryon experiment is also ongoing in the E42 and so on. Okay. Since the time is almost up. Yeah. So this is the last slide, I suppose. So we want to have this hadron hole extension program as early as possible in 2 to 3 years. We want to start this hadron hole extension, and it takes about 6 years for the extension construction program. But by doing so, we have a very good facility for the pi-k high resolution, and also high resolution strangeness -2 spectroscopy and so on. Okay, so this is a summary of my talk. Hadron hole extension will open new decades for hadron physics with new beamlines, HIHR and K1.1, also K10, KL2 or Comet upgrade, together with the existing ones. Revealed role of strangeness in dense matter is the main topics, as well as various hadron physics subjects. We hope to start the project in a few years by carefully schedule optimized ramp run with existing experimental facility and a new one. Thank you very much.
Okay, super thanks to Nagae-san for this very excellent and comprehensive talk summarizing the J-PARC strangeness physics. So we move to the question and discussions. Feel free to raise your hand if you have any question or you want to say anything. Or just feel free to turn on your microphone.
Hi, can I have one question?
Yes.
Yeah, please go ahead, Jinghui.
Yeah, so you have discussed the E70, the K minus bombast, the carbon 12,
Yes.
and try to capture the Borrelian Kazai hypernuclei. So
Yes.
that is still has not happened, right? So
Yeah, that is, we are now in the beam commissioning stage.
okay.
So within a year or so, we want to have the physics data taking.
Okay. So and yeah, I want to ask that, is that possible, or I don't know, is that possible to also use the K minus beam to bombast the light core, for example, the alpha, and to see if this A4 Kazai hypernuclei exists or not?
Wait a minute.
Is there any plan or any possibility also to carry out such a experiment, for example, the K minus and alpha?
K minus alpha? Oh, I see. you want to kick out the alpha particle from the target?
Yes.
Is that your idea?
No, my idea. I just want to see because we also have a fixed target experiment at RIC. So if this carbon-12 that is very heavy, and we will not be able to produce such heavy in high energy. But for the lower mass nuclei, for example, for the alpha, actually we have quite high rate. So that we probably can do it in our data, but we don't know. We don't have signal yet. So we want to ask if this is also possible in your experiment.
I think yes. In principle, we can do it. Yes, but the question is the yield or how much of the such events we can expect or not.
I see. So this is also require for example, fast simulation to understand.
Yeah, I think so. So you want to kick out such a nuclear cluster from the target, right?
Yeah. This is I have a student. We have a student working on this right now. So we probably want to see if there's possible to also check other experiment.
Yeah. So that I think the question is just the yield or how much percent you can expect such a event occurs or not.
I see. Okay. Thank you.
Okay, any further question? Okay, so if no more, probably I think we conclude today's seminar, and we would like to appreciate Nagae-san again. Thanks for accepting and giving us two seminars, and in the now it's almost at the end of this year. We would like to wish you all the best for your life after retirement. And
Thank you. Yeah.
Okay. So hope to still we can meet you or hear from you in the future in whatever conference or any academic activity event, something. Okay.
Thank you.
Bye bye. Yeah, thank you very much.
Bye bye.